Hello, everyone, and welcome back to Math Made Easy. In the previous lecture, we studied Newton's forward interpolation method. We learned how to estimate the value of a function using equally spaced data points, particularly when the required value lies near the beginning of the table. Today, we are going to study a closely related method, that is the Newton's backward interpolation method. The basic idea remains the same. We'll still have a set of equally spaced data points, and we want to estimate the value of the function at an intermediate point. But there is one important difference. So instead of starting our calculation from the beginning of the table, Newton's backward interpolation method starts from the very end of the table. Therefore, it is particularly useful when the required values lies near the last tabulated value. For example, suppose our data range is something like x equals to 12, 10, 11, 12, 13, 14. And now if you want to estimate the value of f13.5, the required point is close to the end of the table. And in such a situation, Newton's backward interpolation method is more convenient than Newton's forward method. So today we will understand the backward differences, the construction of the backward difference table, derivation of the Newton's backward interpolation formula, the meaning of U, and the complete algorithm with a detailed numerical example. So before developing the new formula, let's just quickly compare the two methods. Firstly, the Newton forward used when required x value is near the beginning of the table, and we use hence the forward differences. Now Newton forward used when required x is near the end of the table, and hence we use the backward differences. Both the methods generally require equally spaced x values, and this is extremely important. Now let's just define the backward difference, and the backward difference operator is denoted by nebula. The first backward difference is this nebula yi equals to yi minus 1. For example, if I have this y0 value as 10, y1 as 15, y2 as 22, then this nebula y1 becomes that 15 minus 10 is 5, and this nebula y2 becomes this 22 minus 15 as 7. Now comes the second backward difference. So this is basically denoted by this nebula square yi equals to nebula yi minus nebula of yi minus 1. And similarly, this nebula 3 yi equals to nebula square yi minus nebula square yi minus 1, and so on. And the important point is that the differences are calculated backward from the right hand side of the table. Now consider you have this x and y values, as this x values as 1, 2, 3 and 4, and this y as 2, 5, 10 and 17. Now let's just calculate the first backward differences, that is this nebula y becomes 3, y2 becomes 5 and for y3 becomes 7. Now the second backward differences as nebula 2y2 as is 5 minus 3 as 2, nebula 2y3 as 7 minus 5 as 2. And the third backward difference is nebula 3y3 becomes 2 minus 2 as 0. Therefore, the table can be written as this x value y, nebula square y, nebula cube y. And this x values as 1, 2, 3 and 4. Y as 2, 5, 10, 17. And this nebula y as 3, 5, 7. And this as 2, 2 and hence 0. Now notice where the important values are located. For Newton backward, we use the last row. That is this yn, nebula square yn, and nebula cube yn, and up to so on. And this is analogous to Newton forward, where we use the first row. Suppose the equally spaced data here, we have this x0, x1 and up to xn, with the common spacing as h. For Newton backward interpolation, we measure the distance from the last point as xn. Therefore, this u becomes x minus xn divided by h. Now notice a difference. For Newton forward, we took u is equals to x minus x0 divided by h. But for the Newton backward, we are using this as x minus xn divided by h. And this is one of the most important differences between these two formulas. And hence, Newton backward interpolation formula becomes this yx equals to yn plus u times nabla yn plus u into u plus 1 divided by 2 factorial multiplied by nabla square yn plus u into u plus 1 into u plus 2 divided by 3 factorial into nabla cube yn plus and up to so on, where this u value is x minus xn divided by h. Now, student often asks, like, why does Newton forward contain this u minus 1 and u minus 2 terms, while that Newton backward contains the u plus 1 or u plus 2? The reason comes from the direction in which we construct the interpolation formula. For the forward interpolation, we start from the x naught and move forward through the table. Therefore, the factors becomes this u, u minus 1, u minus 2, and up to so on. For the backward interpolation, we start from xn and move backward. Therefore, the factors become u, u plus 1, u plus 2, and up to so on. So don't try to memorize these formulas separately without understanding the starting points. Just remember this. If there is forward, then just need to start with x naught, and hence become u is equals to x minus x naught divided by h. And hence is u into u minus 1 and u minus 2 terms. And if it is backward, then start with xn. When hence becomes this u equals to x minus xn divided by h, and the terms are as u, u plus 1 or u plus 2 and up to so on. Newton backward is particularly convenient when the x values are equally spaced and the required x values lies near the end of the table. For example, if we have this x values as 10, 11, 12, 13, 14 and we want to estimate the function value at 13.5, then Newton backward is appropriate. But if we want this function value at 10.5, Newton forward would generally be more convenient. Now let's just summarize the Newton backward algorithm fully. Just need to write the given x and y values in a tabular form and check that x values are equally spaced, as is h is equals to xi plus 1 minus xi. Now construct the backward difference table and take the values from the very last row, as is yn, nabla yn and nabla square yn and up to so on. And then calculating the value for the u and hence the backward interpolation polynomial, and hence calculate the required interpolated value. Now we have a question here where we need to estimate the value of function at 4.6 from the data as given in the table, as is x and fx, where the x values are 1, 2, 3, 4 and 5 and the fx values is 3, 6, 13, 28 and 57. Now the first backward difference is 3, 7, 15 and 29. And the second difference is as 4, 8, 14. And the third difference is 4, 6. And the fourth difference is 2. And hence the table becomes as x, y, nabla square y, nabla cube y and nabla 4y. Where this x values as 1, 2, 3, 4 and 5 and y values as 3, 6, 13, 28, 57 and hence this becomes 3, 7, 15, 29 and 4, 8, 14 and then 4, 6 and hence 2. We use the final row only here. We have this yn is 57 and nabla yn is 29, nabla square yn is 14 and nabla cube yn is equals to 6 and this nabla 4 yn as 2. Now just calculating the value for the u, where we have this x value as 4.6, xn value as 5 and h value as 1, hence this u becomes this 4.6 minus 5 divided by 1 as minus 0.4. Now just applying the Newton backward formula here, where we get this y as yn plus u times nabla yn plus u into u plus 1 divided by 2 factorial nabla square yn plus u into u plus 1 into u plus 2 divided by 3 factorial nabla 3 yn plus this u into u plus 1, u plus 2 and u plus 3 divided by 4 factorial into nabla 4yn. Now just substituting all of the terms and the values, we get this y as 57 plus minus zero point 0.4 times 29 plus minus zero point 0.4 into zero point 0.6 divided by 2 multiplied by 14 plus minus zero point 0.4 multiplied by zero point 0.6 into 1.6 divided by 6 and multiplied by 6. Now plus minus zero point 0.4 into zero point 0.6 into 1.6 into 2.6 divided by 24 into 2. Now evaluating all the values and we get this y as 57 minus 11.6 minus 1.68 minus 0.384 minus zero point 0.0832. And therefore this function value at 4.6 becomes 43.2528. So today we started the Newton's backward interpolation method. We learned how backward differences are constructed and how they are used to estimate the value of a function when the required point lies near the end of an equally spaced data table. We derived the Newton backward interpolation formula where we have computed the value for the u, and we also solved a complete numerical example and compared the Newton forward and Newton backward interpolation. Just need to remember the key idea here. The Newton forward starts from the beginning of the table and the Newton backward starts from the end of the table. And both the methods are designed for equally spaced data. And in the next lecture, we will move to the Newton's divided difference interpolation method. Unlike the Newton forward and backward interpolation, the divided difference method can handle unequally spaced data points as well, making it extremely useful when the x values are not equally spaced. We will construct the divided difference tables, derive the interpolation formula, and solve a complete numerical example step by step. Thank you for watching and keep learning, keep practicing, and keep questioning. And I'll see you in the next lecture.